Hello everyone, I'm Vaibhav Gupta, and in this video series, we'll be going over a very interesting concept in the computer science space called quantum computing. With these videos, I aim that we all get a very basic understanding of the quantum computing principles, and I also aim to motivate every one of you regarding why this is going to be the future. If we see companies like Amazon, Google, or Microsoft, they are investing hugely into this space to achieve something called quantum supremacy, which states that we can solve wide horizon of problems much more efficiently and much more faster than any classical computer available. So let's get started by understanding why there was a need to change from classical computing to quantum computing. For that, let's review on our concepts regarding the computation. So as we all know regarding what is computation, so computation is a physical process which is finite in time and it processes information through fixed and distinguishable set of states. Computation is defined by three essential characteristics. The first is information capacity of the system, how much states it has and how much information it can store. The bigger is the information capacity, the more significant tasks we can solve. The second is the speed or the frequency of the state switching. So the faster we can change the states, the faster we can compute, and the faster we can obtain the results. The third is the universality, which all tasks can be solved with a computational system. What horizon does it have? Whether it can only solve some basic arithmetic operations like subtractions, multiplications, or division, or it can just solve the polynomically tiled solve problems, NP problems, or NP hard problems. If we see this complex world with all this new data that we are getting with all the new data analytics approach, we are now seeing the bottleneck in all these three characteristics in the classical computing space. The first is the information capacity. We need to store more information and we need to store in the smaller size. Though if we see our progress in the past few decades, we have improved from storing just certain kilobytes to now multiple terabytes. But still we have a limitation. The technology we are using has improved from the vacuum tubes to the transistors. But how much smaller we can go? Using that PN junction, we can go smaller to certain molecule size. The second is the speed. More speed is required. That is very trivial, but how we can achieve it? We have seen that we have seen the prediction of the increase of the transistors through the Moore's law. But there's going to be a fundamental limit on that. And secondly, our requirement for the speed and for the increase of the speed is much more, it's much greater than what we currently have. The third is the universality. We want computers which should be able to solve all type of problems. But if we say here, the classical computers that we have, we still struggle to solve problems like prime factorization efficiently. And we don't have efficient algorithms for problems like the Hamiltonian path, where if you guys remember that Hamiltonian path problem is a problem where we have to calculate, the efficient path by going through each vertex of the graph once. So these three bottleneck gives us the motivation to go for the quantum computing space, where we say that for the information capacity, now we can go as small as to certain atoms. For the speed, since now we are talking about atoms, we are talking about photons. Now we can have much more faster change of the states and thus faster speed. And the third that we are going to say is the universality. With the quantum computers, we can theoretically say With the general quantum computers, we will be able to solve every type of problem, whether it is a NP problem, NP hard problem, or a NP complete problem. But one thing that happens with the quantum computers when we go that much smaller size is the quantum effect. We can't emulate a quantum system or a quantum effects through a classical system. As Richard Feynman said, that a quantum to emulate a quantum model, we need a quantum system, and that gives us the motivation to go and research to build quantum to explore more of the quantum mechanics and to build quantum computers. And then in the upcoming videos, we'll be going over the basic concepts and the representation of the quantum computing principles. So I'll see you in the next video. Thank you.